Right. So we're going to come up with the ideas to start calculating the work involved with pumping the water out of a cone-shaped tank, and this tank will be said to have a height of 10 meters. So we're going to do this all in the metric system. A base radius of 4, or you could say the top radius is 4. And we're going to say that this thing is filled to a height of 8 meters. So it's filled up here. And we're going to think of the direction in which we move to collect water as this kind of direction. We're pumping water to the top, all the way to the top. That's what we're saying that we're doing, and then moving it out here. And this direction, we're saying that we're 0 meters from the top here. We move down, we're 10 meters from the top, and so this is what this means. Anyway, back to this. The height of this is 10. It's filled up to 8 meters. And I should just put an 8 right there. So from the top to where it's actually filled up, we have a distance of 2 meters. Just 2 meters of empty tank. So let's think of this as follows. Suppose this were a bunch of solid discs. Let's not even think of this as water. Let's just think of a bunch of solid discs. And let's think of these discs as individual things that we... hold on a second. Still getting used to this thing. So, anyway, individual discs that we take to the very top and then just move them out. And so we'll describe these discs as follows. The discs have some radius, and each radius differs depending on where we happen to be. So we'll have this little index here to indicate that for every disc in this tank, where we're pretending these discs are maybe these solid masses, solid blocks that we move, each one of them has its own radius, and each one of them has its own height. So these are just short cylinders. We're going to call this height delta x. It just means, suppose we started at the bottom of the disk and moved to the top, we would have a change in distance. Or if we started at the top, moved to the bottom, we have a change in distance. So change in x, then that would represent height of the disk. So we will assume for this exercise that each one of these has the same height for simplicity. So very thin, bunch of thin disks. Now, of course, let's say the volume and index I for volume. Each one of these will have a different volume because a disk up here of a greater radius than a disk down here, etc. So volume would be base area times height, pi r squared times height, delta x, and then mass of each one. Each one has a separate mass. So index I, we're going to say that we're working in, like I said, metric system, and the density of water, we're going to consider these disks to have the same density as water. So that would be 1,000 kilograms per cubic meter, and so 1,000 pi r squared delta x. So radius is in meters, meters squared, delta x is in meters, so that's meters cubed. And so the mass is 1,000 pi r squared delta x kilograms. And so then what would be the force required to hold this disk in place, statically hold this? I'm not saying force required to move it out of here. Okay, moving this thing up, that's going to be work. Anyway, force involved with statically holding this disk in place right here is then going to be 9.8 multiplied by the mass. And so this doesn't mean miles here. It means index I of mass. And so force for this particular disk indexed by I is then going to be 9,800 pi r squared delta x. So this is force. To calculate overall work required to move all of these hypothetical little disks out of here is basically going to be the summation of all of the individual forces multiplied by the distances that each one of them have to move. And each one of these disks, starting from the top, have to move progressively further and further. And each disk is progressively smaller and smaller. So we want to have some kind of setup that represents both the actual volume based on how far down we are here, then the actual mass and the actual force based on how far down we are from the top. And so then when we can get these actual values of each disk, or from each disk, we can move on to calculate work for each one of them. Force multiplied by distance moved upward. We're not going to think anything about distance moved over here. Of course, this is just an image for illustrative purposes. Okay, so we've got a lot more stuff